Welcome to the lecture for Math 1324 for section 4.1, exponential functions. I've changed up my picture there. I thought I'd show you a more fun picture. This is me hiking. I'm in the Bavarian Alps in the southern part of Germany, probably about 40 miles southwest of Munich. I kind of felt like I was looking like this guy, so I took this picture of me and my wooden twin. Anyway, let's get on with our lecture. Again, I'd like to kind of take a brief pause, and today I want to talk about reflection. So let's look at a couple quotes. Looking back, reflection. Looking back so that the view looking forward is even clearer. Quote by John Dewey, "We do not learn from experience, we learn from reflecting on experience." And a quote by Margaret Wheatley, "Without reflection, we go blindly on our way, creating more unintended consequences and failing to achieve anything useful." I thought this was pretty apropos. We've just finished our first chapter, perhaps, and our first chapter test. And so that's a good time whenever you have kind of a major checkpoint to kind of do a little self-reflection. Self-reflection is so important. But when you're working on a project, you could be looking at how the project is going, how your team is going. Reflection is important for improvement in any area. And so there's a simple tool that I use to just ask myself 3 quick questions. And that is, rocks, sucks, missing. The simple tool is what rocks, and depending upon the topic, you're asking what is helping. What are you doing? What is your team doing that is helping you be successful? What sucks? What are you doing? What is your team doing? What is hurting you or the topic from being successful? And then the last one is what's missing. What could you add? What needs to be added? What could you add to improve performance or success, etc.? It doesn't take long to do this, just a couple minutes kind of to think through and brainstorm each of those, and just to kind of ask yourself to really see how you're doing or in a specific area. And so in this course, it's really good, especially after a test, you see your grade, ask yourself those 3 questions. What did you do really well that was helping you prepare for that test? What hurt you? What didn't you do well? What sucked? What were you doing that didn't help you prepare? And then what didn't you do? What was missing? What could you have done differently? What could you add that will change the outcome? Okay, so let's move on with our lecture. We're beginning a new chapter, and we're looking at exponential and logarithmic functions. Population growth of humans, fish, bacteria, etc., compound interest, radioactive decay, and a host of other phenomena can be described by exponential functions. See exercises on pages 42 to 50. See exercises number 42 to 50 on page 191. Archaeologists sometimes use carbon-14 dating to determine the approximate age of an artifact, such as a dinosaur skeleton or a mummy. This procedure involves using logarithms to solve an exponential equation. See exercises 70 to 72 on page 217. The Richter scale for measuring the magnitude of an earthquake is a logarithmic function. See exercises 73 to 74 on page 217. So you can see there's a lot of actual practical applications of both exponential and logarithmic functions. Almost everything to do with money is an exponential function, whether you're investing it, whether you're borrowing it, etc. A lot of the things, we've seen some things around environmental protection, etc., and bacteria populations, etc. These are usually exponential growths. and of course the Richter scale and the carbon dating are very well-known concepts. They may not be known as exponential or logarithmic, but they are, pretty much well known to everyone in concept, but not how they're actually calculated. Exponential functions. Exponential and logarithmic functions play a key role in management, economics, the social and physical sciences, and engineering. We begin with exponential growth and exponential decay functions. Decay just means that something is shrinking. In polynomial functions, such as f of x equals x squared plus 5x minus 4, the variable is raised to various constant exponents. In exponential functions, such as f of x equals 10 to the power of x, g of x equals 750 times the quantity of 1.05 raised to the power of x, h of x equals 3 raised to the power of 0.6x, and k of x equals 2 raised to the power of negative x squared. The variable is in the exponent, and the base is a positive constant. Okay, this is really key here, that what you're seeing now is instead of x squared, which we're kind of comfortable with, the x, or the variable, is now in the exponent, and that's what makes an exponential function. The variable is in the exponent, and it can be in a mathematical expression. As you saw, it could be 2 to the power of x squared, 2 to the power of the quantity of x plus 1. All of these are possibles. So let's see what happens with these graphs. Graph f of x equals 2 to the power of x, and estimate the height of the graph when x equals 50. So remember that when we have exponents, we like to use positive and negative values of x as input to build a table. And so here we have a table of x and y. The table goes from x equals negative 3, negative 2, negative 1, 0, 1, 2, 3, and then we get the calculated y values. So for example, when x equals negative 3, we get y equals 2 to the power of negative 3. Remember, a negative exponent is a reciprocal, so that equals 1 over 2 to the power of 3, or 1/8, as you can see here. Okay? If we look at the graph there, we see a curve up. It looks like maybe half of a like half of a quadratic. And so as the x values get higher, the curve is getting steeper and steeper. And that's what we mean by exponential growth. We even use it in our language. We talk about that things are growing exponentially, global warming is growing exponentially, etc. So let's continue on. The second part of this question asked us to estimate the height of the graph when x equals 50. This is really kind of more of an impact, and I want you to think about this, okay? So you can see the graph there, and we've gone up to x equals 3, and so 2 to the power of 3 equals 8. But what would happen when x equals 50, okay? Well, at x equals, the graph that we've seen illustrates exponential growth, which is far more explosive than polynomial growth. At x equals 50, the graph would be 2 to the power of 50 units high. Since there are approximately 6 units to the inch in figure 4.1, and since there are 12 inches to the foot and 5,280 feet to the mile, the height of the graph at x equals 50 would be approximately 2 to the power of 50 divided by the quantity of 6 times 12 times 5,280 which would equal 2,961,647,482 miles. Okay? That's 2.9 billion miles. The distance to the sun is only 93 million miles. Okay? So in a very short time, this is saying that the graph paper you would need would be almost 3 billion miles to just draw at the normal, graph little squares. So it's just to show you how explosive this kind of growth really is. It's kind of a fun example and a crazy example, but it really shows you that exponential growth really takes off. And what I want you to pay attention to, we're going to look at the next chapter. This is why it's so important to invest, to save money, because of what we call exponential growth of your income. Is when you invest money, you earn money on the original amount you put in, but also on the amount of interest that you earn. Okay? Let's look at this graph. So when A, and we're talking about when A is greater than 1 on the graph of the exponential function h of x equals a to the power of x. So what we're talking about A here is the base of the exponent. And notice as the base of the exponent gets larger, we see in blue we have 10 to the power of x is the steepest curve. And then in red we have y equals 3 to the power of x, which is not quite as steep, all the way down to y equals 3/2 all to the power of x, which is the flattest curve here. So the higher the value of a, the larger the value of a, the steeper the curve. Well, of course that makes sense, right? The x is our exponent, so 10 squared is 100, where the green curve, 2 to the power of x, 2 squared would only be 4. So you can see the big difference just from that number alone, the difference between the number 4, 2 squared, to the number 10 squared, or 100. Exponential growth functions. When a is greater than 1, again, this a is the base of the exponential function. When a is greater than 1, the function f of x equals a to the power of x has the set of all real numbers as its domain. Its graph has the shape shown on the following page and all of the 5 properties listed below. The graph is the one we've talked about. It kind of levels out at the x-axis on the negative side, and as soon as it becomes positive, it starts shooting upward, growing really rapidly. The graph is all above the x-axis, as you can see in the top right graph. The y-intercept is at 1, because when x equals 0, anything to the 0 power is equal to 1. So a to the 0 power is equal to 1, which is the y-intercept. The graph climbs steeply to the right. It's growing on the right side of the graph very steeply. The negative x-axis is the horizontal asymptote. And the larger the base of a, the more steeply the graph rises to the right. And that's what we were talking about before. If a is 10, it's going to grow a lot faster and be much steeper than if a is 2. Consider the function g of x equals 2 to the quantity 2 raised to the power of negative x. Rewrite the rule of g so that no minus signs appear in it. G of x equals 2 to the negative x power. And then for part b, graph g of x. Okay, well, remember that a negative exponent means a reciprocal. So 2 to the power of negative x is the same thing, or is equal to 1 over 2 to the power of x. Well, if I take, since 1 raised to any power is still 1, if I take that power on the outside, that x power, I can make this 1/2 raised to the power of x, because 1 times 1 times 1 is always going to be 1. That's why I can pull that exponent out of the denominator, because the numerator is 1. I could not do that if it was, for example, 3 over the power of 2 to the x. I can only pull this exponent out because, again, the numerator is 1. So really what we have here, when we have a negative exponent, it's changing the base into a fraction, 1/2. If I had 10 to the negative x, this would be 1/10, etc. So a negative exponent in this case is giving us, for exponential functions, it's giving us fractions functions. If we graph this, again, using positive and negative values, notice we get the reverse graph. It's flipped across the y-axis. Before, where we were growing quickly after we hit the positives, now the growth, it's really, as we move from left to right, we can see that we're shrinking or decaying. The graph is steeply coming down in the negative direction and flattening out along the x-axis as soon as we get across into the positive x values. And this is a graph of exponential decay. The graph falls sharply to the right, but never touches the x-axis because every power of 1/2 is positive. This is an example of exponential decay. When a is between 0 and 1, non-inclusive, when 0 is less than a is less than 1, the function f of x equals a to the x has the set of all real numbers as its domain. Its graph has the shape shown here, which we just saw, which was exponential decay, falling in the negative side sharply and then leveling out in the positive side at the x-axis, and all of the 5 properties listed. The graph is above the x-axis like before. The y-intercept is 1, the y-intercept is positive 1, just because, again, when x is 0, anything to the 0 power is 1. The graph falls sharply to the right. As we're moving to the right, the graph initially falls sharply and then it kind of levels out. And the positive x-axis is the horizontal asymptote. And the smaller the base, the more steeply the graph falls to the right. Okay? So here's that graph, and we can see different values here. So notice that the bottom graph in black is y equals 2/3 to the power of x. That's the largest fraction you see there, and it's the flattest curve. If we go all the way up to the blue curve, y equals 1/10, all raised to the power of x, we can see this is the steepest. So the smaller the fraction, the steeper the curve. The smaller the fraction, the steeper the curve for decay. Okay? When we did growth, it was the larger the number, the larger the growth. When we're doing decay, the smaller the number, the larger the growth. It flips. And don't forget here that y equals 1/2 to the x is y equals 2 to the negative x power, as we just saw in the last slide. So be very mindful of these negative exponents, that they're really indicating, it's the green one there, I just replaced y equals 1/2 to the power of x, so you could see that negative exponent again and kind of hopefully burn that in. A negative exponent is indicating that the base constant is a fraction or decay. So let's look at some problems and see what happens here. First, we're going to look at and compare some graphs. In each case, graph f of x and g of x on the same set of axes and explain how the graphs are related. For graph A, f of x equals 2 to the power of x, and g of x equals 1/2 to the power of x. So what we really have here is 2 to the power of x and 2 to the power of negative x. You can see these. So what we have is an exponential growth and an exponential decay. They are mirror images of each other, and they are flipped across the x-axis. Okay, so a positive and negative exponent flips across the y-axis. I think I said x. This is flipped across the y-axis. Okay, the y-axis acts sort of like a mirror if you looked at that image there, where it cuts it in half. For B, we're looking at f of x equals 3 raised to the power of 1 minus x, and g of x equals 3 raised to the power of negative x. I'd rather write f of x as 3 to the power of negative x plus 1. It's a little bit easier to see there. So here we can see that 3 to the negative x, which is g of x, is a little bit further left. f of x equals 3 to the negative x plus 1 shifts 1 unit to the right. 1 unit to the right. Okay? And the last one we have is f of x equals 2 to the 0.6x, so this is a fraction value in front of the x, versus g of x equals 2 to the power of x. And so here, again, the larger the number, the steeper the curve, 2 to the power of x, that value, the multiplier is 1 versus the multiplier of 0.6. And so we can see that the larger the number, the faster the growth. Okay, because these are both positive exponents, so it's exponential growth. And since 1 is larger than 0.6, that is going to grow faster. Graph f of x equals 2 to the power of negative x squared. This is a great example because students get a little bit confused here about which to do first. For example, if x equals 2, do I make that negative 2 and then square it, or do I square the 2 and then make it negative? Well, remember your order of operations, and exponents come before multiplications. So in this example, you would square the value of x and then apply the negative. Graph f of x equals 2 to the power of negative x squared. Square the value of x and then apply the negative. Okay? So if x equals negative 2, we have 2 to the negative 2 squared. Negative 2 squared is positive 4. Then we apply a negative to that. We get negative 4. And 2 to the power of negative 4 is 1 over 2 to the 4th, or 1/16, as you can see the first value in that chart. Okay? If we graph this, what we have here is almost like a parabola. The values increase to the value of 1, and then so it's a modified parabola, or quadratic it almost looks like, but we still have the x-axis as the horizontal asymptote, because as the values of x get larger in the negative direction or in the positive direction, we just get closer and closer to 0. We never actually hit 0. So here's an interesting concept known as Euler's constant. Euler's constant, almost spelled like the football team. In case 5, we shall see that a certain irrational number denoted by a lowercase e plays an important role in the compounding of interest. This number e, or this number really should be this number Euler's constant, looks like a lowercase e, also arises naturally in a variety of other mathematical and scientific contexts. To 12 decimal places, Euler's constant, or the lowercase e, is approximately 2.7182821828459. Euler's constant is just like pi. It's a number that just continues on and doesn't repeat infinitely. Perhaps the single most useful exponential function is the function defined by f of x equals e to the power of x. This is really crazy. The guy named Euler, who discovered it, was from the 1700s. I'm going to show you a slide about him in a second. But he recognized that in natural growth and in financial growth, like the growth of bacteria, etc., the exponential growth had this really weird base. Now remember, he was doing this in the 1700s and didn't have the TI-84 that you have, and could still calculate these exponential growths, the bases of these out. Okay? So we can see kind of where, because Euler's constant equals 2.7, it would fall between the graphs of h of x, which is 3 to the power of x, and g of x, which is 2 to the power of x. And it should be closer to 3, because 2.7 is closer to 3 than it is to 2. Okay? This number is so powerful in growth and exponentials and money and everything, that it's right up there with pi as far as Google is concerned. You can see this is probably quite old. I imagine Google has 1 million buildings now. But they originally named their buildings E for Euler's constant and pi for the relationship in a circle. So this is a photograph of, well, it's not a photograph, it's a painting of Euler from the 1700s. Leonhard Euler was born in April 15th, tax day, 1707 in Basel, Switzerland. He was one of math's most pioneering thinkers, establishing a career as an academic scholar and contributing greatly to the fields of geometry, trigonometry, and calculus, among other things. He released hundreds of articles and publications during his lifetime and continued to publish after losing his sight. He died on September 18th, 1783. Not a very well-known figure outside the world of math, but certainly his work has impacted our culture and the times we live in, because so much is established around financial management, etc. And all of that's based on Euler's constant. If you borrow money for a home, it's Euler's constant. If you're investing money in a savings account, how it grows is based on Euler's constant, etc. So it's touching you all the time. So let's look at an example here. Example number 5, business. The amount of wine in millions of gallons consumed in the United States can be approximated by the function f of x equals 139.6 e, or Euler's constant, raised to the power of 0.031x, where x equals 0 corresponds to the year 1950. And this is an actual calculation. This is data from www.wineinstitute.org. Now, one of the things I want to point out before we do this problem is when you're reading problems and looking at them, always notice if there's an index. And this is an index. It's saying that when x is 0, we're talking about the year 1950. So when x equals 1, we're talking about 1951. When x equals 10, we're talking about 1960. You have to pay attention to these. For example, the very first question asks us how much wine was consumed in the year 1970. If you're not paying attention to details, the most common mistake I see is that students plug in 1970 for x. Okay? What would we plug in for x? Well, if 0 is 1950, 1970 is 20 years later, so x is going to equal 20. And so I'm going to figure out the value of f of 20. I'm going to use my calculator, and I'm going to get 139.6 e to the 0.031 times 20, and I get approximately 260 million gallons. Remember that the y value is in millions. You would have got the answer 260, but you have to remember that it's in millions of gallons. In 2010, now x equals 60. It's 60 years later. And we get, again, using our calculator, and go ahead and try these. I would try to put these in your calculator just so you get a little practice, 897 million gallons. Now, part C, that was answering the question, how much wine was consumed in the year 2010 for B. For part C, it says, use a graphing calculator to determine when consumption will reach 1,000 million gallons. Okay, now there's a couple ways you can do this. You can put in the formula y equals 139.6 e to the 0.031x, and then go to the table function and look at the y values and keep going down until you see 1,000, see the number y equals 1,000 million gallons. And then you can read over and see what the value of x is there. Now you have to be careful because you probably aren't going to hit it right exactly on January 1st, or when, for example, if x equals 10, that's January 1st, 1960. If it's 10.2, then that means sometime in 1960. And if we're trying to find when x is equal to 10, well, it actually would hit if it hits 10.2 in x equals 10, I'm sorry, I'm confusing myself. If the number, the y value is not exactly a million, then it's going to happen in the year prior, right? So if when we look at the table, well, let's go ahead and finish this example. So what we're actually saying here is, when does this function equal 1000? 139.6 e to the 0.031x equals 1000. So we can put the left side of the equation, 139.6 e to the 0.031x, into our calculator under the y equals function, and then again you go down until we see that. Another thing we can do is we can plug these two formulas in. We could put y equals 139.6 e to the 0.031x as y1, and then we could make y2 equals 1000. Well, the button next to the graph button to the left is calc, and we can try to find an intersection of these two graphs. Now, notice, since the second equation is y equals 1000, we're going to have to make sure that our y-axis goes all the way up to 1000. Okay, and since we're starting at x equals 0 and y equals 0, we can just look at the first quadrant. When you hit that calc button, you'll see a menu there, and one of the menu items is intersection. If you click on that, you have to be able to see both graphs in the window as you see here. What's going to happen first is it says you're on graph 1, and it'll have this bouncing ball that you see at the intersection right now on one of the graphs. And you hit yes or enter. And then that bouncing ball should appear on the other graph, like the curve, for example. And it'll say, is this the second graph? And you say enter or yes. And then it's going to say, do you want to guess? And you just hit enter again, and it will give you the x and the y value. So this says that x equals 63.5 when y equals 1000. Well, what year is that? If I add 63.5, I get, what is that? 50 would be 2000, and another 13 would be 2013.5. So do I round that to 2014? Well, think about it. What is 2013.5? When would that be? Well, that would be halfway through 2013. So technically, we're still in the year of 2013, like somewhere between June and July. Okay, so be very careful with these and be thinking about what those mean, especially when you have decimals on them, like 63.5, and it's representing a year or time. Okay, let's do another example. See if you can do this one on your own using the intersection function or the table function in the graph. I'm going to go through this one pretty quickly because we've been at this a half an hour. When a patient is given, exponential functions, example 6, and this is a health example. When a patient is given a 300 milligram dose of the drug cimetidine intravenously, the amount C of the drug in the bloodstream T hours later is given by C of T equals 300 e to the power of negative 0.3466 t. Okay. If you look at your calculator, there are a couple places where you actually have the Euler's constant. If you look above the divide button, you'll see a little blue e there. So you can always do the second button, which is blue also, and hit divide, and that will give you Euler's constant. If you look to the left of the number 4, you'll see a button called ln, and above that you have e to the power of x. And if you use the second button and that one, it will give you the base e and then a place to put the exponent, which is much easier to use and where you'll use it most often. Okay, how much of the drug is in the bloodstream after 3 hours and 10 hours? So here we're just looking for C of 3, plugging those in, and we could just do this calculation, or we could plug the formula in and look at the table. If I'm asking you for multiple values, it's usually a good idea to go ahead and use the formula y equals button on your calculator and then use the table, so you don't make any, because you can also check that you've entered in the formula exactly correctly, and you don't have any typo errors if you try to type it in a couple times, one time with 3 and then another time with 10. The last question asks us what doctors want to give a patient a second 300 milligram dose of cimetidine when its level is in her bloodstream, when its level in her bloodstream decreases to 75 milligrams. Using graphing technology to determine when this should be done. So we're saying, when does C of t equal 75? Again, we can graph these two graphs. y equals 75, which is the straight line there that you see, the horizontal line, and y equals 300 e to the negative 0.3466t, and then use the calc function and then the menu item for intersection. Here we get 3.9996952 for x and y equals 75. So this is right at 4 hours. So we would want to do this 4 hours after the first dose. And this is actually how dosing is done. And you can see that the exponential decay of the amount in your bloodstream is calculated and figured out to where I want to keep this at a minimal level to treat a patient. That's the end of our lecture. It's a bit long. I apologize for that. But hopefully this helped you, and good luck with the homework, and reach out as you need help.